There, and welcome to BC Calculus. Today, I will be your host, Mr. Giordano. So today, we are going to be talking about a new type of differentiation, and there's a warm-up problem, but I'm just going to kind of show it to you to kind of introduce the lesson. So the warm-up today was going to say this: solve for a, and it was going to be 7xa plus ax squared plus 2x equals 4a plus 7x plus 5. And this skill, in order to solve for a, is what we're going to be doing in today's lesson. And so that's why I have this as a warm-up question, even though it's algebra. But I want us to be able to do this at the very least. So if I'm going to solve for a, notice that there's an a here, a here, a here. And what I want to do is get every term with an a in it on one side of the equal sign, and every term without an a in it, so this 2x, to the other side. So I'm going to do that here. I'm going to move the 4a to the left, 2x to the right. So 7xa plus ax squared minus 4a. And then over here I would have 7x plus 5 minus 2x. So 5x plus 5, if I just subtract 2x over. The whole reason I get these a's on one side is because now I can factor an a out. So I'm going to go ahead and factor an a out of the left side. So 7x plus x squared minus 4 over 5x plus 5. And then the last step, divide by this whole quantity. So a equals 5x plus 5 over 7x plus x squared minus 4. So again, this is an algebra and a pre-cal skill, being able to isolate a variable, but it is the skill that we're going to be working with today. So that leads us to section 2.5. All right, so there are two types of equations. There are explicit and implicit equations. And so far, we've worked with differentiating explicit equations. And I want to explain the difference here, okay? So an implicit equation is when you don't have a variable isolated. You know, most of the equations we do, it'll say y equals x squared plus 5, or y equals 2x plus 5 over x minus 2, or something. It's always y equals something. Well, an implicit equation, for instance, is if you had something like 3x plus 5y equals 10. Here's an example of an implicit equation. Explicit means that it is solved explicitly for one of the variables. Implicit means you don't have a variable isolated. Well, I can take this implicit equation and write it in its explicit form. I can solve for y. You guys have done this since Algebra 1. So I would subtract 3x over and then divide by 5. So I'd have y equals negative 3/5 x plus 2. So again, you guys have done this for quite a while. And then we could find the derivative of this equation right here. The derivative would be negative 3/5 using our basic power rule. Here's another one. Implicitly, 3x squared plus 2y plus 1 equals 0. Implicit because you have x's and y's on the same side of the equal sign. You don't have a variable isolated. So we can isolate the y here. I can get y by itself. I can subtract the 3x squared, I can subtract the 1, and then divide everything by 2 and get y equals negative 3 over 2x squared minus 1/2. So I can solve for y, and now I can find y prime by just doing what we have been doing for the last week or two. Okay, and then this comes along. X cubed minus 3x squared y plus 2xy squared equals 12. And had you been in class, I would say, okay, solve this one for y. And then you would sit there for a long time and you would try to outsmart the problem and try to solve for y and yada yada, and it doesn't work. Okay, and you could pause this and try and say, I'll show you, Mr. Giordano, but you can't get y by itself. Some equations, you just can't turn it into its explicit form. However, we still can find the derivative of this equation, and that's what today's lesson is going to be. How can you take an equation that you can't isolate y, but still find the derivative of it? And it's fun. This is some of my favorite differentiation techniques. I love these types of problems. I know I say that a lot, but I really do mean it. I always mean it. So example 1. Given this equation here, Find dy dx, so the derivative of y with respect to x, explicitly and implicitly. So it wants us to do it two different ways. And the first way is explicitly, this is what we know how to do. Let's go ahead and get y by itself. All right, let's solve for y. So I would probably just add 4y over and then divide everything by 4. And so you would get y equals 1/2 x cubed plus 3/4. So again, I just added 4y over and then divided everything by 4. And now I can find dy dx. dy dx equals, pull the 3 out in front, 3/2 x squared, and then the derivative of 3/4 is 0. So that would be my derivative right here. So not bad. But let's say I didn't solve for y. How else can we find the derivative? Well, here is our technique. Okay, this is a new topic here. We are going to find the derivative implicitly. So here's what we do. I'm going to go ahead and rewrite this equation. Okay, what I'm going to do is take the derivative of both sides of this equation with respect to x. Okay, and so here's what this is going to look like. I'm going to find the derivative of 0 with respect to x. And then I'm going to find the derivative of the right side with respect to x. All right, so the derivative of 0 with respect to anything is still 0. The derivative of 2x cubed with respect to x, when we're differentiating an x term with respect to x, we just differentiate it like normal. The 3 would multiply to the 2, we'd get 6x squared. Here's where the new stuff comes into play. When we differentiate a y term with respect to x, first of all, you're going to differentiate it just like you're doing a normal power rule. Like if I said, hey, what's the derivative of negative 4y? You'd probably say, oh, Mr. Giordano, it's negative 4. And you'd be right. But here's the kicker. Anytime you differentiate a y term with respect to x, after you differentiate it, you have to put and state that you differentiated a y term with respect to x. So anytime you differentiate a y term with respect to x, differentiate it like normal, and then put dy dx to state, hey, I differentiated a y term with respect to x. You don't have to do it with the x terms. You kind of do. You know, think about if I do 6x squared and then I say, oh, I differentiated an x term with respect to x, dx over dx. Well, you don't need to put that. That basically just becomes a 1. But over here, you do need to put it. And then when you differentiate a constant, it goes away. So the new material is when we differentiate a y term with respect to x, we have to put dy dx. And we've been doing that every time anyway. Look up here. When we differentiate this equation, notice what we do when we differentiate the y. We put dy dx because the derivative of y is 1 and then dy dx. So we really have been doing it every time anyway, but now it's going to show up in the middle of the work rather than right at the beginning. Well, now think about what we're trying to find. We're trying to find dy dx. That's the goal. So once we get here, we just have to manipulate our equation to get dy dx alone. So you could add 4 dy dx to the other side equals 6x squared, and then divide by 4. And you should get the same derivative whether you do it implicitly or explicitly. And we do. Right there. So that is the new material. When you differentiate a y term with respect to x, you have to put dy dx behind it. So let's look at example 2a. I have a lovely graph there. Now, you would not be on the hook for knowing that this equation would form this graph. This graph was just in the book, and it looked fun, and so I drew it. But it also will help us graphically understand the answers that we get down here. So it says find y prime. Okay, now obviously we can't solve this for y. We can't solve this for y. But we can now find y prime, or dy dx, implicitly. So what we do, we are going to, I'm going to rewrite the equation. Okay, so you don't have to write this first step, but I do think it helps. You know, it's what I did up here, showing that you're finding the derivative with respect to x. So I'm going to do that to both sides. Now we just go ahead and differentiate each term. The derivative of y cubed is 3y squared. But now we have to say dy dx. We differentiated a y term with respect to x, so we have to state that. Plus 2y dy dx. And then the derivative of negative 5y is negative 5 dy dx. And then we're going to differentiate minus x squared like normal, so minus 2x. Equals, and then the derivative of a constant is just 0. A lot of times students forget that. They'll just leave the minus 4 there, but the derivative is 0. Okay, so now this is why I had us work, well, not had us work, but showed this warm-up problem right here, where you have to be able to isolate something even though it shows up multiple times in the problem. Because that's what we need to do. We have to find dy dx. Well, notice that we have multiple terms with dy dx in it. So any term with a dy dx, leave on one side, and let's add the 2x over to the other side. Then once you accomplish that, you're going to factor dy dx out of all those terms. So I'm going to do 2 steps in one here. I'm going to add the 2x to the right and factor out dy dx. So dy dx times 3y squared plus 2y minus 5 equals 2x. Then I'm going to go ahead and divide by this whole quantity. So dy dx equals 2x divided by 3y squared plus 2y minus 5. So this is the first problem where our derivative not only has an x in it, but it also has a y in it. And I alluded to this a couple classes ago where, up till now, we've only needed the x-coordinate to find the slope of the tangent line. Well, now we need the x and the y. And you can kind of see why over here. Think about why we might need a full coordinate. Because if I say find the slope when x is negative 2, well, there's 3 possibilities. There's one here, you have this slope, or it could mean this here, or it could mean this down here. So we need a full ordered pair to talk about where are we. Notice this isn't a function, and that's why. Typically, this will be done when we have graphs that aren't actually functions. So it says find the slopes of the tangent lines at 2, 0, 1, 1, and 1, negative 3. Okay, so here's some good notation. I think this is pretty good for you guys to know. I want to find... Let me write this up here. There we go. So I want to find dy dx at, so the way we say at, we put like a little bar here. I want to find dy dx at 2, 0. This is notation we'll see show up a little bit throughout this class. That vertical bar is like at or when. So I want to find the derivative at 2, 0, which means we're going to plug 2, 0 in to this derivative that we found right over here. We can do some mental math. Plug 2 in, you get 4 on top. Plug 0 in for the y's, so you get negative 5 on bottom. So negative 4/5 is that derivative. And then I want to find dy dx at 1, 1. So plug 1 and 1 in for x and y here. So 2 over 3 plus 2 is 5, minus 5 is 0. So 2 over 0. Well, that's undefined. Can't divide by 0. That's a no-no. Undefined. And then dy dx at 1, negative 3. Plug it in, so we would get 2 on top. And then, 9 times 3 is 27. Minus 6 is 21. Minus 5 is 16. So 1/8. And the reason I said I have this graph over here, we can kind of check ourselves right over here. So look at what happens at 2, 0. The slope of that tangent line should be negative 4/5. And you can kind of see, it's close to negative 1, which negative 4/5 is. Perfect. Right here at 1, 1, well, look what happens at 1, 1. Think about drawing these tangent lines, and then as you make this turn right here, that tangent line is going to go straight vertical, which has an undefined slope. That's what we just found right here. And then at 1, negative 3, Well, look at that slope. It's positive, but it's really, really shallow. It's not steep, which is what 1/8 is. So it all checks out. Hooray! All right. I'm going to have you guys pause it and maybe try this one, and then I'll put the key on here. So go ahead and try it. Example 3, push pause, see if you can do it. And then when you are ready to see, click unpause. Welcome back. So here is what I got for this problem. Show the work here. I got 1/2. So I found the derivative using implicit differentiation. Don't forget that the derivative of 4 is 0. Instead of putting dy dx, I put y prime. I don't really like that notation. I like dy dx better, but I did it anyway. So I would probably put dy dx if I was going to write this out again. So here's the derivative. And now we need to plug these x and y's into this derivative. Now remember, free response, you can just leave this mess of a expression right here, and that's fine. Some of you probably did that. But if this is multiple choice, 1/2 is probably going to be the answer. And so we really do need to know how to manipulate this expression. So on bottom, I got -4 over radical 2. So I have a negative and a negative, so I just made them positive. And then I have radical 2 divided by this fraction. So I multiplied by that reciprocal. Then that just gives me a 2 over 4. So I'd always, while you can leave things unsimplified, I would always work on simplification. All right, you guys want to try example 4? You want to give it a whirl? Give it a whirl. Try it out. It's more fun that way when you do it. Pause it and then return. Hello. Here's example 4. Again, I did the y primes. I don't like it. It's not wrong. I like the dy dx better, but here you go. So 2x, and then I get 2y dy dx minus 4 plus 6 dy dx, and then the derivative of 9 is 0. Now I need to get any y prime term on one side, the others on the other side, factor it out, and then divide. You can simplify, so just make sure you look to see if you can factor things out, get them to cancel, and that's up to you. And you might have some signs backwards depending on which side you move the y primes to, things like that. But for the most part, I think you guys will be pretty good with simplifying. So it says, find the equation of the tangent line at -2, 5. Well, think about what you need to write the equation of a tangent line. You need the slope. They give you the point. We need to find the slope at this point. So we have to find the derivative of this right here, of this lovely circle. Yes, that is a circle. The center would be at 0, 0, and the radius would be the square root of 29. Just trying to make some connections with equations. So the derivative is 2x plus 2y y prime, or dy dx. Isolate the y prime. Get y prime by itself. So subtract the 2x, divide by the 2y, and then plug in your point. We take our derivative, plug in our point, and then we now know the point and the slope, point-slope form. And for those of you who love slope-intercept form, have at it. I don't know why you would ever do that. There's a word that's, I've never seen it on an AP exam. The word is normal. I do know in physics, just from previous years, students have mentioned the normal force. So I don't know if at this point you guys have talked about that. But a normal line, so it says find the equation of the normal line. That's the line that's perpendicular to the tangent line at a point of tangency. So for instance, if I had, give some curve here. If I had some curve and I said find the normal line at this point here. Well, the first thing I would do is, well, maybe not the first thing, but just so you understand what a normal line is, this right here is the tangent line. The normal line would be perpendicular to that. It would have the opposite reciprocal slope. That would be the normal line to that point. Again, I've never really seen it on an AP exam, but just in case you do, I think it's important that I bring it up. So this goes back to the last problem, right? It's going through the same point as the last problem, but since it's perpendicular, we have to take our slope from the last one and make it be the opposite reciprocal. So these would be perpendicular. All right, last one I'll work through. Unless you want to try it. I mean, feel free to try it. Completely up to you. There is a lot more work on this one, and I don't have a lot of room. So you know what I'm going to do? I am going to do it on a separate sheet of paper. Smart thinking, Mr. Giordano. Thank you. So I have 2x cubed plus x squared y plus y squared x plus y cubed equals 6. And I'm going to go ahead and differentiate every single term. So this is going to be 6x squared. Now, here's the thing. And when you see these come up on an AP exam, and these do, almost always there's going to be some sort of product rule that you have to do, and that is what happens right here. We have x squared times y. So while we're doing implicit differentiation, we can't lose sight of product and quotient that could show up. So here's that case. So I'm going to find the derivative of this term right here. So it's going to be the first, so x squared, times the derivative of the second one. The derivative of y is dy dx, plus the second, which is y, times the derivative of x squared, which is 2x. So I would just have 2xy. This right here is the derivative of that term. I think that's important to understand. That's the product rule. Now I have to do the product rule for y squared x. So plus, so it's first y squared times the derivative of x is 1, so y squared, plus the second times the derivative of y squared, which would be 2y, dy dx. Plus, now we do the derivative of y cubed, so 3y squared, dy dx. And then the derivative of 6 is 0. A lot of people tend to put the 6. They just forget to take the derivative of it. All right. So now I need to get any dy dx on one side and move the other goulash to the other. And I like to do these 2 steps in one. I like to move the terms over and factor out in one step. Saves a line of work. So I'm going to factor out dy dx and have, let's see, x squared plus 2xy plus 3y squared. And then these other terms, the 6x squared, the 2xy, the y squared, I'm just going to subtract all those over. So negative 6x squared, negative 2xy, and then minus y squared. And then you guessed it, divide by this whole quantity, dy dx, and just rewrite this over this. There's your derivative, and then we will be able to find slopes of tangent lines at any ordered pair on that original curve. So that is implicit differentiation, and this is going to kind of lead into our next lesson, which is called related rates. We got some good, fun word problems coming up after this. So now go ahead and try your homework, and I will catch you on the flip side.